Thank you very much for the invitation and the introduction. Yeah, so this is joint work with Haley and Carlo at Imperial College and Omar Fawzi from Lyon. I think he will give a talk tomorrow as well. And indeed, it's a pity that we can't do this in person, especially since I agreed to give a talk here. I moved to Los Angeles, somewhere close to UCLA right now. I'm currently working for Amazon Web Services. I should say though, this is work that is from London, from my time in London, exactly. Okay, so let's get started with a quick motivation slide. So we know from the work of Bell, from the groundbreaking work of Bell, that quantum correlations can be stronger than classical correlations. And what I would like to look at in my talk today is kind of like, how can we make this more quantitative, if you want? Okay, so we can ask, like, how large is the gap actually between classical and quantum correlations? And in particular, I would also like to ask, how does this depend on the underlying dimension of the systems we look at? And I would like to look at it from a computational complexity point of view. So what's the computational complexity of computing these correlations? And there are, of course, many ways of making this mathematically precise, but the way I would like to do it today is via so-called non-local games. And if you want, you can think of this as a computer science approach to Bell inequalities. Okay, so I'll just give you a slightly different explanation if you want what Bell inequalities are. So let's look at them. Let's look at non-local games. And actually, I'd like to restrict myself to the simplest games, if you want. So these are so-called two-proof or one-round games. And here you have two players, okay, Alice and Bob, and they're trying to win a game. And there's a referee that judges, okay? And the setting is such that Alice and Bob, like before the game commences, they can build up any correlation they want. They can have any communication, but as soon as the game starts, they can no longer communicate with each other, okay? And then the referee gives out questions to Alice and Bob, okay? So from some set of questions, and he chooses these questions according to some fixed probability distribution, okay? And then Alice and Bob have to give answers. Let's say A1, A2, they have to give back these answers to the referee, and the referee then decides according to some rule book, okay? So this is just a matrix, a 0-1 matrix that decides if Alice and Bob gave the correct answer or not, okay? So in this setting, the probability distribution with which we choose the questions, as well as the rule book, this matrix V, are fixed. Okay, and then I think a very well-known example is this so-called CH-SH game, or CH-SH Bell inequality. And what we're interested in here is, of course, like, what is the maximum probability that these players can win the game? Okay, and so in this simple CH-SH game, the number of questions as well as the number of answers are all equal to 2. And the questions are chosen uniformly, okay, with the same probability. And then for the CH-SH game has a very special structure. So this rule matrix has a 1 whenever the product of Q1 times Q2 is equal to A1 plus A2 modulo 2, and this rule matrix is 0 otherwise. Okay, so the details of this game don't matter. I just put it because I thought this CH-SH Bell inequality is something people know, and this is how you can phrase it in terms of these non-local games. Okay, and then we're interested in this maximum winning probability. So first of all, we can just look at the completely classical setting. Okay, so what form does this probability, the maximum winning probability, take? Well, okay, so there's this first sum over Q1, Q2. So we just average over the choice of the questions, and then the strategies for Alice and Bob are, well, so these E and D, these are just conditional probability distribution. Okay, so for every question Q1 for Alice, we have to give a probability distribution over all possible answers, and the same for Bob. So this is the most general classical strategy, and one can actually easily show just by the linearity of this objective function that if Alice and Bob would use some correlations, okay, this wouldn't help them. So this is basically a product strategy, but using correlations, classical correlations, does not change the value of this maximum winning probability. And of course, now to bring in the quantum, right, we can ask, okay, what if Alice and Bob have quantum resources at hand? And in particular, before the game starts, right, they could have distributed some entanglement. And so here, in this maximum winning probability, I restrict to a dimension t. So let's say Alice and Bob have local Hilbert spaces of dimension t, right? Then they can use a state rho here, rho t hat, and then their strategy, of course, is not only like choosing a conditional probability distribution, but actually they can perform measurements or more generally POVMs, right? So for every equation Q1, Alice has this POVM ET, and the same thing for Bob again. And then if we want, we can even increase the power more. We can say, oh, actually, we don't fix the dimension of the quantum assistance we give, but we optimize over all dimensions. So this kind of becomes an unbounded problem then, because we can let the dimension increase. And of course, now what I'm interested in is to understand the gap between these three maximum winning probabilities, the classical one, the quantum one for fixed dimension, and the quantum one for an unbounded dimension. Okay, and we can go back to this CH-SH inequality or game if we want. And here, okay, I just abbreviated the notation briefly. So this 1/4, this probability distribution with which we choose the questions, I just take uniform. And then people analyzed this game, and the classical winning probability of this game is 3/4 here. But quantumly, we can actually beat that. We can go all the way to approximately 0.85, and this is actually achieved here already with 2 qubits. Okay, so Alice only needs to use a 2-dimensional system, and Bob as well, and they can already achieve this value better than what is possible classically. And moreover, what Charlson showed is that increasing the quantum dimension actually doesn't help anymore. Okay, so this 2-qubit assisted value is already the unbounded quantum value. So again, this is just one simple example, but now I would like to ask, okay, if we look at general games, if we look at general rule matrices, what can we say then, right? How large can this gap become? Can we compute these values? And so it turns out that these are quite hard problems. So already classically, it's basically a quadratic optimization, right? We have to optimize over this Alice and Bob's strategy each. Already to approximate this value is a hard problem, and very recently there has been this groundbreaking result that the quantum value, it's not even possible to find an algorithm that runs in finite time to approximate its value. So nevertheless, if we look at a special type of games, okay, then we can there are algorithms that approximate the value of these games. Okay, so the details here are not that important. The message here is just that for special type of games, you can actually compute the winning probability or approximate the winning probability. Now, maybe let me just quickly talk about this last bullet point here. So of course, if you want to find lower bound on the winning probability, all you have to do is you have to write down a strategy, right? So for example, in the quantum case, you have to write down a quantum state and certain POVMs that will then achieve a certain winning probability. And so what this NPA hierarchy does is it gives you a way of generating outer bounds or upper bounds on this maximum winning probability. So basically gives you a way to benchmark how well your strategy that you might came up with a good educated guess how good these strategies are actually doing. Nevertheless, in general, it's not computationally efficient, or one cannot prove that it's computationally efficient to evaluate these upper bounds. So, okay, so this was all about the classical and the quantum value of the game. So what I'd like to look at today is this intermediate question, right? So what if we fix the dimension of the quantum assistance? What can we say then? Okay, and I think this question was previously not looked at in detail from this computational complexity viewpoint. So in the rest of the talk, I will talk about this dimension constraint value. Okay, so let's talk about these quantum correlations of fixed dimensions. So here, okay, a small motivation again. So I think whenever we do quantum information processing, we actually have the dimension is often fixed. Okay, so it's actually interesting to understand, you know, what quantum advantage or how strong of quantum correlations we can achieve, and moreover, we can also use this dimension constraint value when we want to construct dimension witnesses. So maybe we have a device that we don't know the dimension of because we don't trust it. Then if we understand this dimension constraint value versus the unconstrained value, this can tell us something about the dimension of the system. Okay. Now, there has been some previous works here, again, some heuristics, how we can approximate this value, how we can generate upper bounds on this winning probability. But if you look into the proofs of this, then the complexity of these algorithms is exponential, okay? And so now, this is our main result now. So we give an approximation algorithm to compute this dimension constraint maximum winning probability. And our main result works for 3 games, okay? This is, again, a special class of games where we choose the questions according to this product distribution. So the questions on Alice's side, that go to Alice and to Bob, they're chosen independently. And then I also put here this symmetric setting, but this is not necessary, so the number of questions don't necessarily have to agree, but it just makes it easier to state our result. And so now if we want to approximate this maximum winning probability up to some small epsilon here, okay, we can do that with an algorithm that has this complexity here, okay? And so the way to think of this is that, okay, we fix epsilon to some constant, let's say. We also fix the dimension of the quantum assistance here with this pretty bad scaling, but then this algorithm runs polynomially in the number of questions, okay? You can see this exp here, outer exp kills this log, okay? And then with this order function here, you get something polynomial in Q. And in A, it runs quasi-polynomially. This is because you have this like log square of A dependence here, okay? So this is an exponential improvement over these previous algorithms. Okay, and in the rest of my talk, I would like to talk a little bit about how we prove this result. And the first step is to make a connection to a well-studied problem, the so-called quantum separability problem. Okay, so here I just wrote down again the objective function of this dimension constraint maximum winning probability. And the first step in our proof is that we rewrite this, okay? So this is now, again, a whole optimization, but maybe just look at the first line here. So there's this prefactor here, t square. This thing here is the maximally entangled state. But what is interesting here is that in the trace here, we now have the tensor product of E, D, and rho, okay? So before, there was this product between rho and this E and D measurement, whereas now we have, so now the objective function is linear in each of these 3 arguments, okay? So one can achieve this with the so-called swap trick. But okay, so it just kind of linearizes the objective function in that sense. And if we keep track of the linear constraints that come from the POVM structure, we get this whole bunch of constraints here. And you don't need to look at the details. Let me just say that these are so-called classical quantum states now, right? Because they're classical on these A and Q registers, because this just corresponds to the register that account for the question and answers. And then they're quantum here on the T register, because these are the POVM operators. Okay, and so now what is nice about this this way of rephrasing the problem here.
A question came up. Marius,
yes, please.
Have you unmuted yourself?
Yeah. So sorry I cannot wait to the end of the talk for my question because I have to teach. So there are 2 comments which I have. So up to a multiplicative content, we asked for this dimension restriction in the work with Palazuelos and all the work by Burman. So this dimension restriction came up, but not in your 1 plus epsilon setting, but in a multiplicative setting.
Okay.
Yeah, so that's just a comment. But does your result imply that these Vivek games cannot be free?
You You mean from his latest works, this uncomputability?
Yes, because I mean, there is some non-computability result, and if you could approximate them in polynomial time, this would contradict computability in general, and essentially they're proving that this is not computable in a certain way.
Yes, so I'm definitely not an expert on that part. So maybe Omar is around, but as far as I understand, so in their work, the games are not free, but there might be a reduction to bring it to free games, but the important part is, of course, here you would have to let t go to infinity. Right. So if you go unconstrained, so then you have the super exponential dependence in t, and this wouldn't.
But I think if it's not computable, then you could. So there is a danger, right? So if these games were free and you would somehow search with a certain dimension, you would know how long you have to search until you get the value approximately right. And if I understand his results, this is not possible for arbitrary games.
In his case, yes. I'm not entirely sure what happens with our algorithm in that case. But
yeah, so it's just maybe it's just a thing you have to think about, but it could show that his things can never be free.
Yes.
Or the reduction is, it could be reduced, but the reduction is not done in reasonable time.
Yes. It's a good question. Yes.
It's very close, right? Sorry.
It's a very good question. No, please. Yeah. Okay, you have to teach, you said, but it might be worth talking to Omar also about this, who knows more about this.
We can do this later.
Results. Perfect. Thanks a lot for the question, Marius. Okay, so I might continue now. So if we look at this way of rephrasing the problem, now we see here that this is a product operator now, okay, in this cut between what Alice has here in terms of the E operator and D for the BOP, and this quantum state, which is on the lives on this copied quantum register. So again, by linearity, we can see that instead of just optimizing here over these product operators, we can optimize over separable operators. Okay, we just have to ask these linear constraints here then for every I. Okay, so for every element in this convex combination, but the value again of the program will stay the same. So what I want to say here is this is now an instance of a well-known problem, quantum separability problem, in particular in this tripartite version, where, however, we have these added linear constraints here, okay? So if you don't know the quantum separability problem, that's fine. It's the problem that you want to optimize over the set of separable states, right? And here it's in this cut, these three-party cuts here. And this, of course, live in this overall Hilbert space. And this is unfortunately a hard problem. However, there are algorithms to approximate the set of separable states, and this actually goes via so-called quantum Finetti theorems. So on a technical level, I now have to talk about Finetti theorems. Okay, so I'm a bit short on time, of course, but so the intuition behind Finetti theorems is that entanglement is monogamous. Okay, so if you have a bipartite state, rho AP, now if you try to share this state amongst not only one B, but many Bs, okay, such that all reduced states are the same, and then this will not be possible if A and B are entangled. And in particular, if you ask that the state is n-shareable for every n, then this exactly characterizes separable states, and we can ask like how fast this conversion is depending on n, okay? This is what the quantum Finetti theorem is, and in particular, so if we have this bipartite states rho AB, and we ask for it to be n-shareable, then we know that this state has to be close to a separable state up to this approximation ratio, which is essentially tight. And now, why is this nice? Well, in principle, this n-shareability is now something that we can check efficiently, whereas separability is something that is not easy to check. However, it immediately comes with this caveat that these Finetti theorems in this approximation factor, you can see you have to choose n exponentially large in B, basically, in order to get a good approximation. And nevertheless, we want to use these Finetti theorems for our setting. However, we now need a tripartite version, and we also need a version that can incorporate linear constraints. And I think I have to speed up here a bit, but basically we now have this tripartite state, and we ask it to be shareable on B and C now. So because we have tripartite, we have to do this shareability in two systems, and then we find that this is close to these tripartite separable states, again up to some approximation here. But moreover, we can also incorporate these linear constraints. So if you have some linear constraints on A, B, and C, then actually every element now in this convex combination can be made to fulfill these linear constraints. And the way to do this is that we have to ask some constraints on this n-shared version of the state, okay? So the details are not important here. Let me just say that you cannot just use a normal Finetti theorem or a normal multipartite Finetti theorem. You really have to think about these linear constraints and how you incorporate them. Good. And okay, so I have to skip the proof, but here is actually where quantum entropy would come in. So the idea is that we're interested in bounding this distance in this trace distance here, right? But by Pinsker inequality, we can actually equally work with quantum relative entropy. And for quantum relative entropy, it's much easier to quantify monogamy of entanglement, because we have all these chain rules how we can shift systems around. And here, okay, there are some definitions here, but the point is we employ these quantum entropy inequalities to prove the Finetti theorem. And one other ingredient we have to use is that we construct these informationally complete measurements that had a minimal loss in information relative to some other quantum side information system. So I don't have time to go into any details about this, but you know, so some systems in our setting, right? The question systems are classical, some are quantum. And with this trick here, we can basically make systems that are quantum classical again, and then go back and forth, and we don't lose too much. We lose this dimension factor, but this is we basically identify this optimal factor. Okay. So now we have our approximation algorithm, and this is it's actually in terms of semi-definite programs. So we have this maximum winning probability omega here, and what we give is a semi-definite program. So this is something that can compute efficiently, that is not too far away from the actual value. Okay, and in particular, the dependence on the number of question and answer here is only logarithmic. Okay, and then this is the form of these SDPs. Let's skip the details here. The point is you can run them efficiently. If you want, you can even add other conditions, okay, to run that. They give better bounds in practice. So for this convergence proof, we only need these conditions, but you can add more conditions if you want. And then indeed, if we look at the complexity to solve this semi-definite program, we end up with this complexity that I claimed at the beginning. And as advertised, this is an exponential improvement in terms of a worst case guarantee. Good. And then this is actually relates back to Mario's questions. And in particular, maybe I was a bit too fast here to write consistent with this non-computability result, but you can basically ask about the T dependence and if you can improve it. Okay, so that's all I want to say. Thank you.